Welcome to the Professor's DuBois channel. This is Professor Corey, and this video is a mini lecture based on our first lecture covering material from Chapter 4. This is in no way equivalent to our actual lecture, where we discuss and practice the material in much more detail. The lecture begins with a brief overview of a few common reaction types. Ultimately, you will apply these patterns of behavior to predict products when reactants are given. The first type is a combination reaction. This is also called a synthesis reaction. A pattern observed is that the number of reactants is greater than the number of products. Some samples are provided. The second type of reaction is called a decomposition reaction. This reaction is essentially the reverse of a combination or synthesis reaction. Decomposition involves a compound breaking down into smaller compounds or elements. The third type of reaction is a displacement reaction, which is also called a replacement. There are two types of displacement reactions. Single displacement reactions involve an element as a reactant. The element reacts with a compound and replaces an element in the compound. If the reactant element forms a cation, it will replace the corresponding element in the compound. Likewise for an anion. This is a good time to mention the subscripts after the elements in the compounds. The letters indicate the state. S is solid, L is liquid, G is gas, and AQ is aqueous. Aqueous means that the compound or element is dissolved in water, making a homogeneous mixture. Double displacements involve switching cations between two compounds. If one of the products forms a solid, we can call it a precipitation reaction. Acids and bases react in the same matter and form a salt and water. Reactions that produce bubbles, which can be observed in aqueous solutions, are called gas-forming reactions. Solutions are always homogeneous. That means evenly mixed. In all solutions, whether gaseous, liquid, or solid, the substance present in the greatest amount is the solvent, and the substance or substances present in lesser amounts are the solutes. The solute does not have to be the same physical state as the solvent, but the state of the solvent determines the state of the solution. We will study aqueous solutions, but realize that other solutions do exist. There are basically four ways that a compound can behave in water. These are listed here. When sodium chloride crystals are dissolved in water or any soluble ionic compound, the polar water molecules exert attracting forces which weaken the ionic bonds. When the process of solution occurs, the ions of sodium and chloride become hydrated. Notice the difference in arrangement of the water molecules as they surround the anion and cation. These differences are due to the unequal charge distribution within the water molecule. The oxygen atom on the water molecule has a slight negative charge, while the hydrogens are slightly positive. The opposite charges create an attraction that enables the water molecules to position around a soluble crystal lattice and essentially tear it apart. Molecular compounds comprised of nonmetals only can be soluble in water, but they do not form ions. Instead, they break apart, but still keep their molecular structure. If you're wondering how we know for certain that soluble ionic compounds form ions while molecular compounds do not, you're really thinking. This is a good question. Solutions formed with ionic compounds will conduct electricity, while solutions formed with molecular compounds do not. You will have to determine if a compound is soluble in water, and this sounds much worse than it is. Molecular compounds will be soluble if they're polar. Water is polar, and a useful phrase for remembering that polar solvents will dissolve polar compounds is like dissolves like. At this stage, we would have to tell you if the compound was polar, so it is unlikely that we will ask you to do this. The solubility of ionic compounds, however, can be predicted based on the ions that make up the compound. These rules are summarized in this table, which will be provided for your exam. To determine the solubility, You will look for an ion from your compound in the column on the left. If it falls under soluble ionic compounds, it may be soluble. You must look to the right and see if there are exceptions. So, a compound containing sodium ion will always be soluble. There are no exceptions. While the presence of a fluoride ion is not soluble when combined with calcium, strontium, barium, or lead cation. Make sure you see the switch to insoluble ionic compounds near the bottom of the chart. The insoluble anions shown all have exceptions. Get comfortable using this chart in practice. We will refer to it often moving forward while we're learning chemistry. Thanks for watching. Please give the video a thumbs up and subscribe if you would like to see more mini lectures on the Professor's DuBois channel.